Hello everyone. Welcome to this week's reading group. Today we will have Dennis Blessing to talk about a scalable diffusion sampler, bridge matching sampler. Dennis is a PhD, a third-year PhD student in KIT. His research focus is mainly on variational inference and scalable sampling method, and particularly on diffusion-based sampling method. Actually, from my side, I think Dennis has did a lot of great work on diffusion samplers. He has advanced this field for to a great extent. So we are very glad to have Dennis to talk about his recent advance in this field. Yeah, thank you, Dennis.
Thank you, Chichen. As I already got a notification that my internet connection is a bit unstable, so I will turn off the camera. I hope you can hear me fine. So just let me know if something. Okay, so thanks for the introduction. So I will talk about our recent work, bridge matching sampler, which is a scalable algorithm for training diffusion-based sampling methods. So this is zip and data to the burner from NVIDIA, and my student Eva and supervisor Gary from KIT. And I want to talk about our goal samples, or as an unknown reference mutation history, where we have access to some kind of energy function.
It seems that Dennis lost his connection. Hello, Dennis.
Can you hear me?
Not quite.
Okay, sorry. Let me switch the room. Maybe it's getting better then.
Yeah, no worries. I can see your
Is it?
screen now, but I can't. Yeah, your voice is very lagging, but the screen sharing is yeah. I can see your
I'm
screen.
ve I'm very sorry about that. Yeah, unfortunately, I can't be at the office right now. I hope it's better now. I changed the room. Can you
Yeah,
hear?
it seems to be better now. Yeah.
Okay, okay. So should I start from the beginning, or did you hear what I said?
I guess I missed the beginning. Maybe brief is yeah.
Okay. I mean, I was just like briefly talking about the setup. So, um, yeah, I mean, I guess we focus on the second task here to sample from an anomalized density. Um, and yeah, so we don't assume any data from the target distribution, but only access to the anomalized density. And so two like typical settings include sampling from a Boltzmann density where we have some energy function E, for example, the Boltzmann density of a molecule. Or recently gaining more popularity is fine-tuning of generative models, where we assume access to some kind of pre-trained model and some reward function, and we want to sample from the tilted distribution. And here the reward function, for instance, can encode human preferences, and then the goal would be to better align with what humans thinks is good. And one thing I want to mention is that in this data-free setting, we need to kind of explore the support of our target density by ourselves, which is in contrast to the data-driven setting where the support of the target is kind of implicitly defined by the samples that we have in our data set, which makes this problem very challenging and also especially in high dimensions. So here we study the classical sampling problem, where we have access to an unnormalized density, and we just want to generate samples from the target density. And so one of the classical ideas is to evolve the samples using some kind of tractable Breyer from which you sample, and then evolve those samples using a stochastic differential equation, such as Langevin dynamics, where we just follow the gradient of the target density. And so here we have an example. So we start with a Gaussian, and then we let our SDE evolve our samples, and we can see that the target density on the right is a two-dimensional, two-mode GMM, which we kind of approximate quite well. And then we can slightly shift the weight of the modes, and then we can see that it already starts to get worse. So we can see that one mode is getting a lot of samples, which it shouldn't, and the other one is getting too few. And we can take this even further and shift the target density, and then we can see that our approximation is getting worse and worse. And this is because Langevin only has asymptotic guarantees that if we let our SDE run forever, we can get equilibrium samples from this distribution. And so the idea of diffusion-based sampling is mainly to use kind of controlled process. So here we just add a control to this Langevin dynamics. And by adding this control, we want to achieve these finite time conversions that we can obtain samples from the target distribution within a finite time. But then the main question is, how do we learn this control such that we can achieve that? And so this is kind of the whole idea of diffusion-based sampling, that we learn this control in order to get samples from the target distribution in finite time. And so here I want to introduce diffusion-based sampling from a very general perspective. Consider two controlled SDEs. So one is controlled by some drift U and starts from the prior distribution. And the other one starts from the target distribution at a terminal time and runs backwards in time and is controlled by some drift V. And now the goal is to kind of adjust these control functions U and V such that X and Y are time reversals of each other, which would then imply that the samples from X from our forward process X are coming from the target, and that the samples from the backward process are coming from the prior. And so here we also illustrate this. So we start with a Gaussian again. We have this two-mode GMM, and then the process X runs forward in time, and the process Y runs backward in time. And so our goal is to kind of align these two processes. And we can look at this from so-called path measure perspective. So we say that this process X induces a path measure controlled by U, which we denote by PU, and this backward process induces a path measure V, which we denote here by PV. And we can think of these objects like joint distributions over an infinite dimensional space or over the space of continuous trajectories. And then we can use those kind of obtain this variation perspective by minimizing divergences between those path measures. And if we manage to get this divergence zero, then we know that we solved our original sampling problem because we have time reversal, and we can use our optimum control U in order to sample from the target distribution. And here we also illustrate this. So we have some distribution pi, which we show here in red, and some distribution tau in blue. And then we see that we have, like on the left side, we see that we have some random trajectories. And then after we minimize a divergence, we have this kind of transport between pi and tau. And so one observation is that this likelihood ratio, which is also often referred to Radon-Nikodym derivative, is tractable, meaning we can actually implement this on a computer and minimize those divergences. And so some of the popular choices for divergences in early works were the KL divergence, where we just compute the expectation of this this log ratio. But this has some major drawbacks. For instance, we require simulation for every gradient steps, which kind of prevents us from reusing samples that we already generated. And this kind of makes it very difficult to scale this to larger problems. And we also need to differentiate through our SDE solver, which can also be prohibitive for high-dimensional problems. And lastly, the gradient computation relies on the entire trajectory. So in order to make one gradient step, we have to solve this integral over the whole time of the diffusion process. And this can also make it challenging to scale this to larger problems. Then there were two alternative divergences, which were more popular later on, which is the log variance loss and also trajectory balance loss, where you can kind of minimize these divergences using arbitrary samples that come from some process that is controlled by W, which can really be arbitrary. So you can use off-policy samples or replay buffers. And by having this property, we don't need to differentiate Fourier SE solver anymore. And as I said, we can reuse samples, which is quite nice for sample efficiency. But one problem still remains is that we need that the gradient computation still relies on the entire trajectory. So these expressions in the expectation and the variance are operations over the entire time window, which also makes this challenging to scale this to larger problems. So to conclude this, I would say that trajectory-based approaches lack scalability. And so to kind of address this, we can go one step back and ask the question, what makes these database approaches so scalable for optimizing diffusion models? And so for that, I want to make a quick detour and look at like a common perspective on recent database approaches. So we can typically characterize the optimal drift either from an SE or an ODE as a conditional expectation of some path-dependent drift psi. And this can directly lead to an objective for optimizing the control by realizing that the conditional expectation is just the minimizer of a regression objective. And so this is kind of the principle that underlies flow matching or stochastic interpolance or bridge matching. And another thing that we kind of require is that given pairs x0 and xt, we can sample intermediate states tractably. And we can also do this, for instance, with stochastic interpolance or flow matching, where we just sample, for instance, a linear path. And we can see this here. So we have our stochastic interpolant, which allows us to sample intermediate states. And so in the paper, they showed that if we define psi in a certain way, then the conditional expectation of this psi yields the drift that kind of solves this transport plan that we want to solve. And so one question that we can ask is if we can transfer these ideas to the sampling problem in order to achieve more scalable algorithms. And this is kind of the idea of adjoint sampling, which was published quite recently. So I think it was ICML last year. And so the authors kind of motivate this from a stochastic optimal control perspective, where they say that we're given some stochastic optimal control problem of the form that we want to minimize the norm of our control, and we have some terminal cost G. And then one can show that the optimal control satisfies, again, some conditional expectation, which is just the gradient of the terminal condition, and then scaled by the negative of the diffusion coefficient. And by using this insight, we can directly write down a regression objective in order to obtain the optimal control. But the main problem here is that the expectation is taken with respect to the optimal control process, which we don't have. I mean, that's what we want to learn in the first place. And so that's a problem. And so what the authors then propose is to use a fixed point iteration where they say that instead of using samples from the optimal control, we just use samples from the current control. And for now, we can just ignore this projection operator here. So we just define this fixed point iteration where our expectation is over the current samples, and then we regress onto this terminal cost G. And then they show that if we have a fixed point, then we are exactly at the optimal solution. And so this is really awesome because now we can use a lot of these concepts that we have for the database setting and apply it to the sample-based setting, right? And so the first work that was coming out last year was from Ricky Chen's group and other people from Meta, which they called adjoint sampling. And for that, they used that the terminal cost is the log of the terminal distribution of the uncontrolled process or base process, which is tractable, it's just a Gaussian, and then divided by the target density. But there we had some additional constraints, and mainly that we require our base process to be memoryless, meaning that the initial and terminal states are independent, and So one way to achieve this is just by setting the initial distribution to a delta. But this can be very limiting in practice. And this is why they had a follow-up work, which they called the adjoint Schrödinger bridge matching sampler, where they set the terminal cost to this ratio between the Schrödinger potential phi hat and target. And the cool thing about this work is that you can really use any prior and any target distribution now, which is quite awesome. But the main problem here is that the Schrödinger potential is unknown. And so we have to additionally learn this in every iteration. And so what can also be problematic in practice is that if we learn a bad approximation of the Schrödinger potential, then our control is directly affected by that because it's part of the terminal condition, which is then part of the regression objective for our control. And so the question that we asked in our recent work is if we can construct a sampler that also works for arbitrary prior and target distributions, but then does not require these alternating optimizations, but also retains the scalability of adjoint sampling and adjoint Schrödinger bridge sampling. And so first we can ask, what do we actually want from our sampler? And so one thing that we mentioned earlier is that we want to be able to sample from, so given some pair of X0 and XT samples, we want to be able to sample states in between in order to avoid like having to compute losses over whole trajectories. So we want our target measure to be of the following form. So we want that it decomposes into a coupling between our between samples X0 and XT and this conditional process, which you can sample tractably. And we also require the coupling to have the boundary constraints that we start at the prior and we end at the target distribution. So by marginalizing out the final states, we arrive at the prior, and marginalizing out the initial states, we arrive at the target. And here, this conditional distribution relates to a bridge process, for instance, the Brownian bridge. And this we can sample tractably, and because it's just a Gaussian. So then, given some samples X0 and XT from our coupling, we can sample from our target measure by using that the conditional distribution is Gaussian. And so the specific form of this target measure is very related to something that is called reciprocal classes, which I will briefly formalize here. So we say that a path measure is in the reciprocal class of this reference process P, which we assume to be tractable, like that we can tractably sample the conditional process. If it satisfies its decomposition into this coupling and the conditional. And we can also define the reciprocal projection of such a process by taking the path measure as input and then just outputting this coupling of the original path measure and then using the conditional of the reference process. Okay, great. So now we can also just generically write an SDE where we say that this satisfies that this has the same margins as the target measure pi star. So we say that some target measure, for instance, the one that we prescribed above, which can, for instance, be non-Markovian, can be represented using some non-Markovian SDE. And so the idea that we had in this work is to kind of Markovianize this process using something that is called a Markovian projection, which I will formalize now. And so the Markovian projection of some non-Markovian path measure pi star is a Markovian path measure that is controlled by some U star such that the marginal of these two processes coincide. And we can also relate this to the optimal control by, again, just identifying that U star is then the conditional explication of the non-Markovian drift psi. And also we can find that this is equivalent to minimizing the forward KL. And if you find such a control U star, then we know that we solve the sampling problem because by construction, we said that the initial and the terminal marginals of pi star are the prior and the target. And since the Markovian projection is marginal preserving, we know that we start at the prior and end at the target. So now we have two challenges for computing this optimal control, which is the conditional expectation of this non-Markovian drift psi. First of all, we cannot sample from the target measure, pi star, because that's our goal. And we don't know this non-Markovian drift psi. And for addressing the first problem, we just use the same solution that that work in edge-on sampling did. So we just define a fixed point iteration. So instead of directly using samples from the optimal one, we use samples from the current one and regress onto the path dependent drift psi, and then we repeat this. And the current, so pi I here is again the reciprocal process of our current coupling that we obtained by using our current control. And the second challenge that we don't know psi will be addressed now. So in order to derive this, I will briefly sketch how we derive this in the paper. I want to recall the setting that I introduced earlier about diffusion-based sampling. So we assume that we have some forward SDE that is controlled by U and some backward SDE that is controlled by V. And our goal is to achieve time reversal to solve our sampling problem. And there's something that is called Nelson's duality relation, which kind of relates the drifts U and V and the score, and which tells us that the optimal distribution, the optimal control is equal to the score minus the backward control. And then we can use something that we derive in the paper, which we call generalized target score identity, to obtain a conditional expectation expression for the score and the Markovian projection for the backward control V to give us another expression for a conditional expectation. And then we can combine those two by writing them in one expectation. So we have the expectation of pi star here of psi s minus psi v. And by combining those, we get an expression for psi, which you can then use to perform our fixed point iteration. And so just to briefly state this, so the psi for general couplings looks the following. So we have the gradient with respect to our initial condition of our coupling. Then we have the gradient with respect to the terminal state of our coupling. And then we have some additional score of a transition density, which is also just Gaussian. Okay, and so maybe just to briefly summarize what we did is we now derive the formula for psi for general reciprocal classes that give us an expression such that the conditional expectation of this psi is the optimal control. And since this is the Markovian projection, we know that our marginals of the controlled Markovian process coincide with this potentially non-Markovian measure pi. And now we can make different choices for this coupling to obtain different algorithms. So one of the first choices could be Schrödinger half bridges, where we set the setting as the coupling to an independent coupling between the reference prior and the target distribution. And then the expression that we obtain for psi using our previous proposition leads us exactly to the regression objective that is used in edge-on sampling. Then we can consider full Schrödinger bridges where we use the Schrödinger bridge coupling, which depends on these Schrödinger potentials, phi hat and phi. And then, interestingly, this just leads to exactly the regression target that we used, that edge-on Schrödinger bridge sampling uses. And then lastly, we can consider independent couplings where we say that the target coupling is just independent between some prior coupling, pi star 0, and the target pi t 0. And so this gives us this new psi, which we use for our new sampler, which contains the score of the prior of the target and then the score of this conditional transition kernel. And we call the resulting method a bridge matching sampler because it has the same fixed point as bridge matching. Okay, so maybe a brief summary as to how the algorithm looks and to make this a bit more graspable. So we start with some initial control U0 and we kind of specify a number of iterations and then we iterate the following steps. So we simulate a bunch of trajectories and then we can make a choice of coupling for the different algorithms. So if we want to use ASBS, we just take the coupled pairs that we have on our control. If we want to use adjoint sampling, we just take independent samples between the reference prior and the samples that we obtain by the control. And then if you want to use our sampler, we just use the independent couplings between our controlled process for the time 0 and time t. And then we can store those samples in a buffer to be more sample efficient. And then we compute the reciprocal projection of this measure. And then after that, we perform the fixed point iteration or Markovianization, what you call it here. And this is just a regression objective then. And then we repeat this until convergence, and then in the end, we return the control, which is hopefully close to the target. Okay, and here also some a small illustration. So given some prior and some target, we simulate our controlled process and obtain these prior target pairs, which we then project using this reciprocal projection and sample bridges in between. And we use those to kind of regress onto this psi that we derived, and then we repeat this process. And by regressing onto this psi, we computed like a Markovian projection of the current control process. And then if you repeat this, so we have kind of a Markovian process, we simulate it, we get samples, we perform a reciprocal projection, then we optimize, get a new Markov process, and then we repeat this until we converge. And so here we don't need to simulate trajectories in every gradient step. So it's enough if we have prior target pairs. Sorry, not prior target pairs, but prior pairs with the samples from our current control. And then we can kind of generate an infinite amount of data using these couplings. And crucially, the loss function doesn't need entire trajectory for gradient steps, which also leads to highly scalable algorithms. And so one extension that we did in this paper is that to stabilize the training, we can consider something that we call damping, where we have this, instead of just performing the fixed point iteration that we introduced earlier, we partially reuse the old control by using this convex combination between the optimum of the fixed point iteration and our previous control. And we can directly find a variation characterization of this by having this regression objective where we regress onto the psi that we derived, but we also have this weighted loss where we regress onto the previous control. And this parameter eta, which you call damping, is related to this alpha for this damped fixed point iteration. So it's kind of a way to stabilize the training. Exactly. And so since we have this very general framework, we can apply this damping also to adjoint sampling in ASBS. Okay, so let's look at the performance. So and start with some toy target densities. So here we look at GMMs with 20 modes in varying dimensions and using different damping parameters. So we start by 100 dimensions and go up to 2,500 dimensions. And so what we observe is that for ASBS, which is on the left, we get for low damping values, so for 0 and 1, we get very unstable results and the algorithm mostly diverges, which is why we put NA there. And then if we increase the damping, we achieve much more stability and manage to kind of increase the dimensionality while getting some decent performance. But we can also see that this bridge matching sampler seems to be much more stable especially it works without damping, but also if we increase the damping, then we see that we have almost no performance loss, even if we increase the dimensionality to rather high dimensions. And also one thing I should mention is that most sampling methods kind of struggle with these GMMs already in 20 to 50 dimensions. So going up to 2,500 dimensions was really surprising that this still works that well. Here we also have a Gaussian mixture model in 100 dimensions with 100 modes, and we can see that it still works quite nicely. And we can also look at the training curves for ASBS and the bridge matching sampler for different damping values. So for low damping values, as we saw in this heat map earlier, the ASBS diverges, which you can see here on the left. And then for larger damping values, it gets more and more stable. And the same thing we observe for the bridge matching sampler, that the higher the damping, the more stable it gets, but also the longer it takes to converge. Okay, so next we looked at some n-body particle systems. So we had this double well with 4 particles, Lennard-Jones with 13 particles, and Lennard-Jones with 55 particles. And we benchmarked against the same methods that were in the ASBS paper and compared it to those results. And we found that it works really well, even though we don't have to do a lot of tuning. So we can also look at the interatomic distances and the energy histograms. And yeah, they look quite good, I would say. And lastly, we also looked at some peptide systems, for instance, alanine dipeptide, which has 66 dimensions or 22 atoms. And so one thing that I want to mention is that so we kind of learned a system in Cartesian coordinates, which was, to the best of my knowledge, not really possible before. Um, exactly, and here we see the Ramachandran plot, so which is kind of a histogram over the backbone angles. And we see the reference and D data on the left. And then we always have 2 plots here, so 2 for ISBS and 2 for our method, and one uses no damping and the other one uses some damping that help to stabilize the training. And we can see that with the damping we get much more much better results, and they are much closer to the ND data. And here we also looked at the Tika plots. And here we also see a similar behavior that with damping, they are much closer to the ND data. And yeah. And we also looked at alanine tetrapeptide. And here again, the Ramachandran plots for different residues. And we see that the approximation gets a bit worse. So we always observe this oversmoothing, which is quite interesting because usually samplers suffer from mode collapse, but here it's actually quite the opposite, that we oversmooth the target density. Which is quite interesting. And so currently we think that it's mainly caused by the architecture that we use. Okay, then here we also have some training dynamics that we plot for alanine dipeptide. So we see the bridge matching sampler and ASBS for 2 different damping values. And here again, we can see that the damping really stabilizes the training. And here also more quantitative results. So we look at the Jensen-Shannon divergence over the backbone angles, the MSE over the free energy landscape, and also the Wasserstein distance for the Tika plots. And especially for alanine 4, we didn't manage to get the methods to work without the damping, where both of the methods diverged. But using the damping, we were able to get some decent results for both of these methods. And yeah, Thanks a lot for your attention, and I'm happy to take any questions.
Thank you so much, Dennis. Yeah, it's time for questions. And also, if you don't want your voice or questions to be recorded, we can stop. We can ask questions after I stop recording. Or if you're fine with that, you can ask now.
For me, it's also fine. We can leave it in.
Ben, do you have a question or it's a
Yeah, I have a question. Thanks
okay?
very much for the really awesome presentation and very cool work. I think getting those results is extremely difficult, so well done. I wanted to ask, I missed, unfortunately, the beginning. I had two questions. One is, would you mind explaining how the Markovian projection is? It seems as though it's almost sort of trivial and very tractable for you. I just I don't understand it. And the other question is, you mentioned that you have this oversmoothing as opposed to mode collapse, and I think that that is also extremely interesting and very yeah, I'm surprised by the result. Is there something in the objective that you think would lead to that, or you said it's the architecture? I'm just curious if you have any more thoughts there.
Hi, Ben. Sorry for the first question. I wasn't fully sure if I understood it correctly. So should I briefly go over the Markovian projection again, or?
Yeah, that would be great if you don't mind. I didn't quite understand because I guess the notion is that you essentially project onto the Markovian, you have a Markovian projection, and then you do regression on the control to the Markovian projection. Is that correct?
Yeah, let me just briefly go there. So I think the main idea is that you here we prescribe some target measure which you call pi star, which is typically non-Markovian. So we can kind of express it as a non-Markovian SDE, which we call psi here. So we said that it's so this non-Markovian SDE induces this non-Markovian path measure pi star. And then the Markovian projection of this gives us a Markov control which has the same marginals. So if pi star has the target and prior as the boundary marginals, and we compute the Markovian projection of it, we preserve those marginals. So I guess that's the idea. And the way we can compute this is by using the conditional expectation of this non-Markovian drift psi.
Ah, okay, I think I understand. Okay.
And yeah,
Okay.
sorry.
So the idea is that at every time marginal, you have a trajectory that you created essentially during a sampling process, and you want a new process that's Markovian such that the drift is equal to sort of the conditional expectation of this psi at time t.
Right. So you wanted those margins aligned because you prescribed the target measure in a way that you can kind of tractably sample from the bridge. So you only need to have samples from the coupling, and then you can sample from the conditional, right? You can sample from the Brownian bridge, for instance, which makes the objective very scalable. And by having this property, you can kind of scalably compute this conditional expectation and to compute the Markovian projection of this psi to obtain a Markovian process that has the same marginals and basically solves the sampling problem. So does that make sense?
I think I need to take a more look at it because I guess the thing like this path measure here, uh, can you describe it more? The conditional one, where you have two endpoints and you have set up a Brownian bridge. But I guess I just would have thought that the Brownian bridge is Markovian, but maybe I'm
No, the process that corresponds to a Brownian bridge has the terminal sample in there because it's conditioned on the terminal. And it starts from x0, right? So it's dependent on both endpoints. So in that sense, it's
good
not
point.
non-Markovian.
Yes, I see. Makes sense. No, thank you. That makes sense.
And yeah, regarding your second question, I think it's quite interesting. So I currently suspect that I mean, sorry, one thing I have to mention is that the Markovian projection is a forward KL, right? And we know that the forward KL is mode seeking. So I would expect that some of the properties carry over to the fixed point iteration so that the objective is more mode covering than mode seeking.
That makes a lot of sense.
So that's one thing. And the other thing is that so the objectives only use the score, right? So we only regress onto the score. We don't have any information about the energy landscape itself in the objective. And there is some interesting work that show that the score is actually kind of blind towards the different weights of the modes and the target density. So this could also be a result. So this oversmoothing could be a result of that, so that we don't have the information about the energy landscape and it take very, very long to converge to something that is kind of learns the right portions. Because if you look at the if you look at the 1D marginals over these backbone angles, you can see that it's always moving and it's slowly going down, but then sometimes it's just stuck. So I'm not sure. It could also be. I mean, I think it's a combination. I think if you use better architecture, it could also help to improve this, I would say.
Thank you very much. Really, really cool work.
Thanks.
Thank you for the question. Are there any questions regarding to the talk?
Yes. Thanks for the work. Maybe a very quick one. So assumes right now you have some samples, like data samples. Is it easy to incorporate, for example, pre-train the velocity field or vector field, then fine-tune using your algorithm, or in general, you will not see any improvement? What's the trade-off here? How to combine with some data samples and pure energy-based training?
Yeah, so we haven't looked at database training because we were purely focusing on energy based. So also all these results are purely from energy. So there is no pre-training or anything like that. But I think the cool property about these objective is that they're actually forward cal. So you can directly use them for database training. So for instance, if you look at the formula here, so this Markovian projection is essentially forward KL. So if you have samples from your target density, you can use the same objective for training from data. So I think it's like the most seamless transition from database training to fine tuning, because you can use essentially the same objective. So the only thing that changes is that instead of using samples from your current model, you use samples from the data distribution or from your data set.
Okay, thanks. Very nice. Because I also saw like a joint sampling paper. They also try to pre-train on something, and then they find out, okay, if you pre-train on samples, then you get the best result. Actually, yeah. I'm a bit curious on this. Yeah, thanks.
We still have time for more questions. Or I will stop recording.